So let's prove the first part, and let's prove the reverse implication first, which is that f equal to 0 mu almost everywhere implies that the L1 norm is equal to 0. So first note that f equal to 0 is equivalent to saying that mod f equal to 0 for any point x. So let me take x here. So then it's enough to show this property for unsigned measurable functions. So it suffices to show this for unsigned measurable functions, because once you show it for unsigned measurable functions, you can do it for real valued functions and then for complex valued functions as well. So let's show this first for unsigned measurable functions. So if f equal to 0 for mu almost everywhere, and so first we suppose that f is simple, so we can do this easy case first. So let me write f as a finite linear combination of indicator functions for measurable sets ei. So these are measurable sets. So then f equal to 0 mu almost everywhere implies that for each I, either alpha I, the value of f, is equal to 0, or the measure of ei is equal to 0. So this implies that the simple integral of f, which is the same as the Lebesgue integral of f, this is equal to the sum alpha I mu ei, and this is going to be 0. So it holds for the case when f is simple. Now if you take any positive simple function which is bounded above pointwise by f, then f equal to 0 mu almost everywhere implies that s equal to 0 mu almost everywhere, which means that the simple integral of s d mu, this is 0 by what we have just shown. And so the supremum of all such simple functions is going to be 0, and this is nothing but the integral of f. So we have shown that for unsigned measurable functions, when f is 0 almost everywhere, then the L1 norm is going to be 0. So now I leave it as an exercise to show this for, as an exercise, show this for first real valued and then complex valued measurable absolutely integrable functions. This is x, f is in L1 x mu. By breaking these real valued functions in positive and negative parts and using the unsigned case, and then using for the complex case, breaking it into real and imaginary parts, and then using the real case. So I leave it as an exercise. Now to prove the forward implication, which is that if f has the L1 norm 0, then f equal to 0 mu almost everywhere. So note that the set of points for which fx not equal to 0, it's a union a countable union of these sets f. So let me write again mod f, because if we show that mod fx equal not equal to 0 has measure 0, then f equal to 0 also has measure 0. So mod f is greater than or equal to 1 over n, and so if we write these as En, it suffices to show that the measure of En equals 0 for all n greater than or equal to 1. So let's see what are these measures. X in x says that mod fx greater than or equal to 1 by n, and this by the Markov inequality, if you take lambda to be 1 by n, then you have 1 over lambda, so n 1 over n, so n times the L1 norm of f, and this is 0, so this is 0. So this implies that mu of En equals 0 for all n greater than or equal to 1, and this shows that this exceptional set where the modulus is not equal to 0. So let me write this as E is 0. So this implies that the measure of E0 is equal to 0, which means that this implies that the set of points for which mod fx is equal to 0, or rather mod fx equal to 0 mu almost everywhere, and this is equivalent to saying that fx equal to 0 mu almost everywhere. So we have shown that if L1 norm is 0, then f equal to 0 mu almost everywhere. So this shows the first part, and now let's see what was the second part. So if f is an unsigned measurable function, then f is finite mu almost everywhere. So for the second part, we have to show that if f is an unsigned measurable function, and f belongs to the L1 absolutely integrable function, which is the same as saying that this integral d mu is finite. So then we have to show that the set E infinity, which is the set of points such that fx is equal to infinity, has measure 0. So notice first that this set E infinity can be written as an intersection over all positive integers of the sets x in x such that fx is greater than or equal to n, and if these sets are, I denote En, then by Markov's inequality implies that the measure of the set En is less than or equal to 1 over n times the L1 norm of f, and since E infinity is a subset of En for all n greater than or equal to 1, this implies that the measure of E infinity is less than or equal to the measure of En, and this is less than or equal to 1 over n times the L1 norm of f, and this goes to 0 as n tends to infinity. So this means that the measure of E infinity is 0. So we have proved these two properties in the corollary. As a remark, I note that if f is finite mu almost everywhere, then this does not imply that f belongs to L1 x mu in general. So for an example, you can take x to be R and mu to be the Lebesgue measure on R, and f to be the identity function which gives you x. So we know that this function is unbounded, and so f does not belong to L1 of Rm, even though f is finite actually everywhere here, but even if you leave out any null set, we also have f is finite almost everywhere for the Lebesgue measure. So the converse for the corollary, the second part of the corollary, does not hold in general. Now let's look at another important inequality called the triangle inequality, and it says that if f is an L1 function, then the modulus of the integral of f is less than or equal to integral of the modulus, which is nothing but the L1 norm. So the L1 norm bounds the modulus of the complex valued integral of f. So let's see a proof. So first, if f is real valued, then the modulus is nothing but the modulus of the positive part minus the negative part, and these are two complex numbers, so this can be written as less than or equal to integral f plus d mu plus the modulus of f minus d mu. But note that these two are already positive, so you can remove the modulus because they are both positive, and so this is equal to f plus f minus d mu, and this is nothing but mod f. So this is equal to mod f d mu. So if f is real valued, then it is then it follows from the usual triangle inequality for complex numbers. In fact, real numbers here, because these are real numbers, positive real numbers. So we have proved this for the case when f is real valued. Now if f is complex valued, we use that if z is a complex number, then z can be written as e to the I theta modulus of z for some real number theta. So similarly, we can write the integral f d mu as e to the power I theta modulus of f d mu, because this belongs to the complex numbers. So this is for some theta in R. So this implies that the modulus of f d mu is equal to e to the power minus I theta integral x f d mu, and by using the linearity property, using the for complex scalars, now this is equal to, you can take this complex scalar inside the integral, so you get e to the power minus I theta f of d mu, and now you can take the real parts on both sides. So taking real part on both sides. So on the left hand side it is already a real number because we have taken the modulus, so it does not change, and on the right side we have the real part of e to the power minus I theta f d mu. But the way we have defined complex integrals, the real part of the complex integral is the integral of the real part. So this is nothing but the real part of e to the power minus I theta f d mu, and now this is less than or equal to mod f. So this is less than or equal to modulus of f. So we have shown that this also holds for complex valued L1 functions. So now we come to a very important theorem called the dominated convergence theorem for L1 functions or absolutely integrable functions. So we have seen that we can use the monotone convergence theorem for unsigned measurable functions to interchange the limit and integral, and the dominated convergence theorem gives you sufficient criteria when you can interchange the limit and integral for complex valued L1 functions. So let's see the statement of the theorem. So let Fn n equal to 1 to infinity be a sequence of L1 functions. So here I am abbreviating absolutely integrable functions as L1 functions, absolutely integrable functions. This is L1 functions in short. So if you take a sequence of L1 functions such that first condition is that Fn converges to f, a function f, mu almost everywhere, and secondly that there exists an unsigned measurable function, unsigned measurable function g, which is also absolutely integrable or integrable, such that all these fn's, the modulus of all these fn's is bounded above by g, again mu almost everywhere. So then the statement of the theorem says that then we can interchange the limit and the integral sign, which means that the integral, so first that f is in L1 and the integral of the complex integral of f is equal to the limit as n tends to infinity of the integrals of fn, and here again this is a interchange of limit and integration, because on the left hand side you have the limit inside and here you have the limit outside the integral on the right hand side. So this is called the dominated convergence theorem because we have a dominating function g, dominating L1 function g, which bounds all these fn's, and this guarantees that your limit is going to be L1 and you can write the limit, the integral of the limit is as the limit of the integrals. So here we use the technical condition that our measure space is complete. So let me just write it here. So we let x be mu be a complete measure space. So this holds for complete measure space because we have seen that for complete measure spaces a sequence of measurable functions converging almost everywhere to another function gives you a measurable function. So we need this completeness business, but once we have that, it's not very difficult to establish the proof. So first note that f is measurable since it's a limit of measurable functions. It is a limit almost everywhere of measurable functions fn. Secondly, we also have the modulus of f is equal to the limit as n goes to infinity of the modulus of fn, and this is bounded above by this function g, and this is an L1 function. So f is in fact an L1 function. So now we are only left to show that the integral of f d mu is the limit of the integrals of fn d mu. So first note that it suffices to show this for real valued functions only by taking real and imaginary parts for complex valued functions. So it suffices to show this for real valued functions fn and f. So we assume that all the fn's are real valued, and all and the limit f is of course again real valued. So then we have that modulus of fn is less than or equal to g. This is given. This implies that minus g less than or equal to fn is less than or equal to g. So fn lies between minus g and g, and this implies that first that g plus fn is positive and g minus fn is also a positive function. So now we are going to apply Fatou's lemma. Applying Fatou's lemma. So remember that Fatou's lemma was only applicable for unsigned measurable functions. So we are going to apply it for both these functions g plus n to g plus n fn and g minus fn. So first, if we take g plus fn, we will get integral lim inf of g plus fn d mu as n goes to infinity is less than or equal to lim inf as n goes to infinity integral of g plus fn d mu. Now this is nothing but g plus f, because this is the lim inf and the lim sup of fn both. So in particular it is equal to the lim sup, f is equal to the lim sup. So the lim inf of g plus fn is equal to g plus f. So this implies that integral g d mu plus integral f d mu, by using linearity I am writing it as two integrals g d mu plus f d mu, and this is less than or equal to the lim inf as n goes to infinity integral g d mu plus integral fn d mu. But this first one does not have any dependence on n, so you can take this lim inf inside. So this is equal to integral g d mu plus lim inf n tends to infinity fn d mu, and now we can cancel these two g d mu's integral because these are finite. So since integral g d mu is finite, this implies that integral of f d mu is less than or equal to lim inf n tends to infinity integral fn d mu. Similarly, we can use it, we can apply Fatou's lemma for Fatou's lemma for g minus fn, which is again a positive sequence of functions, and for this we again have lim inf n goes to infinity g minus fn d mu is less than or equal to the lim inf as n tends to infinity integral g minus fn d mu. And now we take the negation on both sides, so negate on both sides, and we use the fact that lim inf n tends to infinity with a negative sign of some sequence a n is equal to lim sup n tends to infinity of minus a n for any sequence of positive real numbers a n. So here we will get minus integral of lim inf n tends to infinity g minus fn d mu is greater than or equal to minus lim inf n tends to infinity integral g minus fn d mu. And so now we can use this fact here about lim sups and lim inf when you take the negation. So this is nothing but integral lim sup n tends to infinity minus, or rather fn minus g d mu, and on the right hand side you will get lim sup n tends to infinity integral x over x fn minus g d mu. But on the left hand side the lim sup of fn's is simply f, so you get integral f d mu minus integral g d mu, and on the right hand side you get lim sup n tends to infinity integral of fn d mu minus integral of g d mu. But now this function g is an L1 function, so these terms are finite, the integrals are finite, so they cancel out, and this implies that integral over x f d mu is greater than or equal to the lim sup n tends to infinity of fn d mu. So in total we get that the lim inf of fn d mu n tends to infinity is greater than or equal to the integral f d mu, which is greater than or equal to lim sup n tends to infinity fn d mu. And because we always have, since lim inf n tends to infinity fn d mu integral is less than or equal to the lim sup fn d mu, this implies what we need, which is that the integral of f d mu is equal to the lim sup or the lim inf and the limit. When they are all the same, we just write limit lim of fn d mu, and this is the proof of the dominated convergence theorem.